In this session, we want to look at what you have been waiting for all this time. That's the mass spectrometer itself. Right? This session has been on mass spectrometer, has been the title, but then the instrument is not that we are ready to do that. But why are we doing it now? Because we wanted you to understand relative abundance, because that's what we use the mass spectrometer to do, to evaluate. So mass spectrometer is basically the instrument that will help you to actually calculate those relative abundances and all that. So we want to go through the process and understand how different parts of this instrument come together to make sure that we're able to evaluate the mass relative abundances and then be able to calculate the relative atomic mass of elements in general, right? So this is the instrument that we have. We have a picture of it. We have 5 different versions, but then they all have the same part. They play the same basic roles, which we want to look at. So let's look at the various parts of this thing. So here there's an entry point. So there's an entry point here. I'll circle this side. That's the first part. And then there will be another thing when the entry, whatever enters, right? There will be an operation happening here. And then there is another section that will be within these 2 plates. Another section, and they will be interested in what happens here too. And they're also interested in whatever happens finally over here. So there are about 1, 2, 3, 4, 5 different compartments. I'll call it compartments or different chambers. So they usually call them chambers but different compartments, because not everyone can be called chamber, right? Some of them are just the name of the instrument that's there. Okay, so now let's label these parts. The very first part, right? So the entry point, here they say gas sample. So we may have different things, as I said, but then there's actually a particular box here. Something happened before this gas enters. This arrow is showing that an entry point of a gas sample. So there's a sample gas, a gaseous sample that they inject into this, and then the rest happens, right? But then actually, for most of the figures, you'll be seeing a chamber here that will be producing the gas. There will be a chamber here that will be producing that gas that will enter this tube. This particular thing, we call it vaporization chamber. So the very first thing is the vaporization chamber. Don't mind my handwriting, right? Vaporization chamber, that's the very first chamber here. So that's the chamber that changes the sample. Whether the sample is usually in powder form, in liquid form, or in solid form. This chamber will be able to make it vapor, turn it into vapor. Vapor is gas, right? So the vaporization chamber is basically to convert whatever the sample is into a gaseous substance, right? So it's to vaporize the sample. Vaporization, that's what happens. So convert the substance from whatever form it is, whatever state it is, to a gaseous form. Now, there's another sample here. Now, we know that over here, a gas sample is entering here. So you can see some gas sample here. Here is a gas sample entering here. So whatever is going to happen here is going to be ionization. So we are going to ionize the gas. So here is going to be ionization of the gas. So we call it ionization chamber. Here, this is a chamber where ionization of the gaseous sample works. So here, listen to me, ionization of the gaseous sample. So you have to know firstly that the thing is in gaseous form before it is here. So whatever happens in this ionization chamber is the ionization of the gaseous sample. Okay, so how does it occur? So there is something here called electron beam, that's at the bottom here, and then there's a heater. There's a heater here. So this heating element, this particular electron beam, it throws a beam of electron, meaning very high speed beams of electron into the gaseous sample. That's what happens here. So let me make it bigger, right? So let's say the gaseous sample is here. It is gaseous sample. It's atom. It's an atom actually. There are a lot of atoms placed inside that gas, right? And then we have our electron gun. Let's say it's here, like shooting. This one is shooting very high speed electron into this. A very high speed electron into this. And then this electron is so fast that to pass through the gas and hit another plate here, which is the heating element at the top here. So the shooting electron, this guy will be shooting, it's like gun, shooting the electrons, and the electrons will be passing through the gas and will come in here and stick at the top here. So why are we shooting electrons into this? So what happened is, we said these things are what? there are a lot of atoms inside. So these atoms contains neutrons and electrons, right? So what we are trying to do is that these high-speed electrons, right, will be able to knock off some of the electron from this gaseous sample. We want to make sure that the gaseous sample, the atoms inside, we are able to remove some of the electrons from them. So we shoot very high-speed electrons into the sample so that this when these high-speed electrons are passing through the gas, they'll be able to knock or collide with some of the electrons that are already in the atom, right? And take and push them along. So it's as if you are throwing a ball against another ball, but this one is very high speed. So the one that is coming with high speed will not stay in the sample, but it will help to knock off another one, and all of them will get out of the gas, right? At the end of the day, to make the gas atom, the gaseous sample, right? Some of the atoms or the atoms here, the sample here become ionized, become an ion. Because you say ion is formed when what species lose electron. So when they are losing electron, when a particular species is releasing an electron, we say it is going to be a cation. It's going to be forming a positive ion because we are losing electrons. So we are shooting electron into it so that the electron will knock off some of the electron from the gas sample. At the end of the day, the gas sample that was originally came will now lose some of the electrons. When it loses some of the electrons, now lots of electrons will result into a cation or a positively charged ions. So in the ionization chamber, what basically happens is that the gas sample is changed into positive ions. So now positive ions are now formed here in the gaseous sample, right? You say ionization, but you form ions there. So by shooting beam of electrons, and these electrons, this beam of electrons will knock off some of the electrons from the gaseous sample. At the end of the day, the gaseous sample will lose electrons. When the gaseous sample loses electrons, it becomes a positive charge ion. This positively charged ion is now called the positive charge ion. That's it. These are cations. So cations are formed in our ionization chamber. Now, after forming the positive ion, now they are charges. Now that they carry charge, the carriage of charge and the carrying of charge will make them now be influenced by two fields. We need them to form ions because we want them to be affected by two fields. It can be charged particle can be affected by electric field. It can also be affected by magnetic field. So we are doing this to change them into ions first, so that the fields ahead or the chambers ahead, they contain electric field and magnetic field. So these ones will be able to act on these species. So because if they don't come in ion form, they are not going to act. They are going to be neutral. They're not going to work. So what will happen is that we need to do this ionization to change them into gaseous species, ionic species, right? Positive ions especially, so that the field ahead, the chambers ahead will be able to work on them. Because if you are charged, either negative or positive, electric or magnetic field will act on you. So let's see what happens ahead. Now we all understand that we have positive ions coming from here. Now these are plates. Two plates are here. This particular plate, we are going to call it acceleration chamber, right? So what happens is that the electric plate, this actually, we are not going to call it chamber, this electric field. We are going to call it electric field. So this is an electric field. So the first one, this is the electric field. This guy's ions form an ion, right? Now there are two plates here. Now these positive ions now will now be attracted. This electric plate, this plate will now attract the positive ion because they have now acquired charge and there's electric field. So electric field is very hungry for these charges. So what happens is that when the positive ions are formed, right, it will not be attracted here. So this plate will attract them and then accelerate them onto the next field. So it will attract the positive ions and then accelerate them onto the next field. This you can see that's what happened here. The next field is this field. So the electric field is actually basically doing what? Attracting the positive charge ions, attracting them. It will attract them first and then push them to the next one. So we say that the electric field attracts the positive charge ions and accelerates them into the next field. What's the name of the next field? Magnetic field. So yeah, that is the name is even here. Magnetic field. So the next field is magnetic field. So we have electric field that will attract the positive ions and accelerate them into the magnetic field. That's what we have here. Now, what is the magnetic field doing? Magnetic field now will curve them, will now deviate them. There will be deviation happening here. The magnetic field will be able to deviate charged particles. If you are charged particle, magnetic field will be acting on you, and this is how they act on you. They are able to deviate your path. So they are deviating according to their mass to charge ratio. So the mass to charge ratio of the sample. Remember, these are ions that are coming. We form the ions in the ionization chamber already. And each of these ions are different atoms. And the different atoms, we see that they have different masses. Isotopes of the same element, they have different atomic number, right? And by the same mass number. So they will be now the magnetic will now disperse them into different parts, direct them into different parts onto the detector. So those of equal mass, if these of equal mass will now, let's say these people on this line will have equal mass and they will be here. Those on the other mass will also be here, like that. So all based on the mass, right? You follow some path, you undergo some deviation and you follow a path in the magnetic field and fall on the detector. So the detector will be able to measure, because let me say the detector is this plate here, and then the things are coming from the top here, right? So those atoms in the species that are having the same mass to charge ratio, they will all fall on the same place. Let's say first atom, second atom, third atom, fourth atom, fifth atom, sixth atom. Then this one also come. This is the first one. So this pass two, some will come, some will fall here. Let's say 3 here, 4 here. And then let's say this one, 0, 2, yeah, like that. This one will also fall down, maybe 1. So what will happen is that you'll be able to know that, okay, these are the same atoms, but then they are different isotopes of the same elements. These are the different isotopes of the same element. So those that are having the same masses will fall here, same masses will fall here, so same masses will fall here. So you'll be able to know how abundant this particular isotope is in the species. You'll be able to know this, how abundant this one is also is, how abundant this is, and how abundant this is. So you use the abundances. So all of them will be 100%. You calculate the relative abundance of this guy, and you know the mass of this, the ones that are falling here. The ones that are falling here, you'll be able to use the detector to see the mass. You'll be able to see the mass of those that are falling here, and then you use their occurrences on each graph, right, to be able to detect the relative abundance. So now you'll be able to get the relative abundance, and you'll be able to get the mass of each. Then you go back to the formula to calculate the relative atomic mass of the element will be the sum of the product of the mass times the relative abundance all over the sum of all the relative abundances, like how we used the previous section to calculate. You see, now the scenario that happens in the mass spectrometer. So let me quickly go over everything quickly. So what basically happens in each field? What basically happens in each field? It has to come to understanding. It has to come with understanding. So yeah, I have taken time to explain what happens here. So here there is the sample gets here. We inject the sample here in the vaporization chamber. In the vaporization chamber, and the vaporization chamber will change what? We change the sample into gaseous form. That's what the vaporization chamber. We change the sample into gaseous form. That's what we call it. So, or it will vaporize the sample. So now that vapor or that gas will now enter the tube and be able to enter the first flow. This first flow, what should happen? Now the thing is sample is not gaseous. When it's not gaseous, it's entering the flow. The next first thing is that we need to change it into ions first, so that the electric field and magnetic field ahead will be able to work on them, will act on them, or may affect them. So when the sample gets in first, the very first chamber it meets is the ionization chamber. So in this chamber, we throw beams of electron. We shoot beams of electrons into the gaseous species in order to knock off some of the electrons, and then this will leave the gaseous species positively charged. Once it gets positively charged, the electric field is closed. This electric field will now attract them and accelerate. It attracts and accelerates the positive ions into the magnetic field. This is what this guy does, into the magnetic field. And what will magnetic field do? The magnetic field will now deviate these accelerated ions, positive ions, especially these are very positive ions, according to their mass to charge ratio, into semicircular parts. So the part here is semicircular. It's not fully circle, but then they are going to deviate them into semicircular part. It's not really fully circular, but semi. There's a portion, right? Semicircular part. We deviate them onto the semicircular part, onto a detector. And what will the detector do? The detector will record the relative abundances and then the masses of the various isotopes inside the sample. Then we use that to calculate the relative atomic mass of the entire species. That's what we have. So we have vaporization chamber, then we came here ionization chamber. Then after you ionize, what should happen? Acceleration. We have push it to magnetic field. So electric field will come, then magnetic field will take over by deviating them into the detector, and the magnetic will now separate them into their various parts of the detector. And on the detector, we'll be able to measure the masses and the relative abundance to actually evaluate the relative atomic mass of the sample, whatever sample that we put inside. So this is how mass spectrometer is able to help us to do all these things easily. So you inject, you come every, but it's very good to understand what happens inside, right? So we can say mention the chambers and their role. Vaporization chamber, right, to vaporize the sample. Then after you vaporize, what should happen next? So we have to now ionize it. The very first thing you enter is you ionize the sample. After you ionize the sample in the ionization chamber, what happens? The electric field will take this ion because the thing is now ionized. So electric field is hungry for ion. So once you see ions near it, to attract them and accelerate them to the magnetic field. Now the magnetic field will now deflect these positively charged ions or accelerated ions into a semicircular part onto the detector, and on the detector we'll be able to read and record the relative abundances and masses, which will help us to evaluate the relative atomic mass of the substance. See you in the next session.